Our work so far in transmission lines has really been about characterizing what happens to the voltage and current for a sinusoidal signal that's traveling down the T-line, and we've shown that we can characterize this through what we call the characteristic impedance and the propagation velocity, or sometimes we characterize it between the characteristic impedance and the complex propagation constant of the system. What I want to look at now is what happens when we connect a load to a transmission line and we create an impedance boundary between that transmission line and that load. So for this analysis, we're going to kind of redefine our normal geometry. We're going to put the load along the z-axis, and we're going to say that that is the 0 point on the z-axis. So that means that everything to the left of the load is on the minus z-axis, and so the total length of the transmission line, if this transmission line is L meters, its input is at minus L along the z-axis. That we're still considering that a positive traveling wave is moving right from the left side to the right. So if we were to plot the total voltage and current on the transmission line at any given point, or not plot, if we were to write the total transmission line voltage and current in phasor form, hopefully this is starting to look familiar to you. You've got the phasor voltage is equal to this positive traveling wave amplitude and phase, e to the minus alpha plus j beta z plus v bar minus e to the plus alpha plus j beta z, and that's in volts, and the current phasor is equal to I bar plus e to the, and then exactly the same exponents. And that's in amps there. So, and what you'll recall from this is that this is the total forward traveling wave going this direction. This is the total reverse traveling wave, and we had previously shown that all the voltage and current along a transmission line can be represented by the sum of two sinusoidal functions, one going this direction and one going this direction. So what's the voltage at the load? At the load, Z is equal to 0. So the voltage at the load is going to be at Z is equal to 0. And in a like manner, the current at the load is going to be, when we evaluate these equations, at Z equals 0. So by definition, ZL, the load voltage, has to be equal to, the load impedance has to be equal to the load voltage divided by the load current. So if we were to plug Z is equal to 0 into this equation and this equation, we would get ZL here. So we'll do that. So we've got V bar plus e to the minus alpha plus j beta times 0 plus V bar minus e to the alpha plus j beta times 0 over I bar plus e to the minus alpha plus j beta times 0 plus I bar minus e to the alpha plus j beta times 0. So all these exponential terms are going to go to e to the minus 0, e to the 0. So that goes to 1, that goes to 1, that goes to 1, and that goes to 1. And so that leaves us with ZL is equal to V bar plus V bar, sorry, I left off the minus sign there, V bar minus over I bar plus I bar minus. So that's the relationship for the impedance at the load right there. By definition, which we showed in a previous video, Z0 is equal, the characteristic impedance of the transmission line is equal to either the relationship to the forward traveling voltage to the forward traveling current, or the opposite of the reverse traveling voltage to the reverse traveling current. And so I can solve both of these equations for I bar for the current, and that gives me I bar plus is equal to V bar plus over Z0, and the reverse current is I bar minus is equal to minus V bar minus over Z0. So I'm going to plug these two values in to this equation right here, and we find out that the load impedance is equal to V bar plus V bar minus over V bar plus over Z0 minus V bar minus over Z0. And now all I'm going to do is I'm going to pull this Z0 out of the denominator, so I could pull it out here, it'd be 1 over Z0, but since this is in the denominator, it's going to flip, and so that's going to be equal to Z0 times V bar plus V bar minus over V bar plus minus V bar minus. So I've got this relationship here. Now what I want to do is solve this equation, ZL equals Z0 times this multiplicative term here for V minus, and that takes a minute of algebra, so I'm just going to give you the result. V bar minus is equal to V bar plus times ZL minus Z0 over ZL plus Z0. So what that is saying is that the amplitude of this the amplitude and phase of this reflected current waveform is determined by the amplitude and phase of the incident waveform times ZL minus Z0 over ZL plus Z0. So how big this guy is and how much phase shift it has is really dependent on the difference between ZL and Z0. And so we give that thing a very important name, and we call this term right here, the reflection coefficient at the load, gamma sub L. And by definition, V bar minus is equal to V bar plus times the reflection coefficient. So if we solve for reflection coefficient, we get that that is equal to V bar minus over V bar plus. So a lot of times you'll hear the reflection coefficient is the ratio of the reflected voltage waveform to the incident voltage waveform. So what we're saying is if an incident wave V bar plus encounters an impedance mismatch, a wave must be reflected at that impedance mismatch. That's what that math is telling us there. One thing to note about the reflection coefficient here is that it is a complex number. A lot of times we'll drop the indication that this has a magnitude and a phase associated with it, but it really does. And what that means is not only does it cause a reflection in the of the incident voltage waveform, but it can also phase shift the incident voltage waveform reflection. So if we were to write this out, you know, the reflection coefficient has actually got a magnitude of the reflection coefficient, and it's got some sort of phase angle associated with it. So for example, let's say, well, let's hold off on the example for right now. I want to point out one more thing. Reflection coefficients don't have to be at the load. We can measure the reflection coefficient at any point along the transmission line, and we would call that the reflection coefficient as a function of distance along the transmission line. And really that's just it's equal to the magnitude of the reverse voltage wave at Z equals D, or actually minus D from our setup up here where this point 0, over the forward voltage wave. at z equals minus d. And we could do a little bit of math to show it, but I'll probably just save you the time and give you the results that if we plug z equals minus d into the equation for reverse voltage and forward voltage, you end up with the result that the reflection coefficient at any point along the transmission line can be calculated by taking the reflection coefficient at the load and multiplying it by e to the minus 2 alpha plus j beta, and then the distance along the transmission line that we're looking at. So for a lossless line, this can get reduced to the reflection coefficient at any distance is just going to be reflection coefficient at the load, e to the minus 2 j beta d, which is often how you see it written. If we were to put these results into polar form, it's just going to be the magnitude of the reflection coefficient at the load times or at an angle of whatever the original reflection coefficient angle was, minus 2 beta d. So to show what that actually looks like, I want to calculate the reflection coefficient at different distances along a T-line for a 50 ohm T-line connected to 150 ohms. And we want to do it at the load, so 0 meters. We want to do it at z equals lambda over 4 distance away from the load, and z equals lambda over 2 distance from the load. I'm writing distances as fractions of lambda because remember wavelength is in meters, so we can specify distance as fractions of a wavelength. So the reflection coefficient of d is equal to 0 is just the reflection coefficient at the load, and that's going to be zl minus z0 over zl plus z0. That's 150 minus 50 over 50 plus 50, or 150 plus 50. And so we get that that's 0.5. More specifically, we could write that as 0.5 plus J0, which is the same as 0.5 at an angle of 0 degrees. Lambda, or reflection coefficient at lambda over 4, is therefore going to be 0.5 at an angle of 0 minus 2 times beta, which is 2 pi over lambda, that's just the formula for beta, times the distance d, which I specified as lambda over 4, which I think you might see why I did that now. And that's going to give me 0.5 at an angle of 0 minus pi, 0.5 at an angle of minus pi. That means at a distance of lambda over 4, the reverse wavelength is half the amplitude of the incident wave and has been phase shifted by minus pi radians. Finally, we've got the result. Let's look at lambda over 2. And so that's going to be 0.5 at an angle of 0 minus 2 times 2 pi over lambda, which is just beta, times whatever our distance was, lambda over 2 in this case. And so that's equal to 0.5 at an angle of minus 2 pi, which is just equal to 0.5. And so at a distance of lambda over 2 back from the load, the reflection coefficient is returned to its initial value.